Good morning, Srikanth.
Hey, good morning again. How are you?
You're doing good. So I think you forgot to share the Python file. I think you shared it just few minutes back.
Yeah, I just shared just now. Okay, so hopefully you might have received. I just shared it couple of minutes back.
Yeah. Just saw it.
Yeah. So just remind me if I forget. Okay, sharing. So when I go to office, so I'm in a different world altogether.
Yeah. So Srikanth, this SVM, it's
Yeah.
generally used when you have a lot of categories, correct? Whenever,
Yes.
data set have,
Data
multiple
when
variety.
data set is huge and your objective is to get high accuracy. At that time, SVM is the better model to choose.
Okay. Okay. So yesterday, I think towards the end, you discussed that epsilon and the cost function.
Yes, yes,
So you said the cost function will control the misclassification and all. So
yes,
in that, you're saying generally when we go, we should go that it should be 80 to 90 by 80 to 90% should be classified correctly. So that we get the optimal hyperplane and all. So that is the
right,
most
right,
important thing.
right. So see, if you go with a high cost function, as I've shown that it will not allow any misclassification. So what will happen is that it will try to come up with a hyperplane which not allow any kind of misclassification. So what will happen that you will get 100% accuracy on the training data, and you may not able to get a better accuracy on your test data. So that may lead to an overfitting problem, right? So in that case, and that may happen because there could be some kind of an outliers, as I mentioned yesterday, right? So there could be some exceptions, there could be some outliers because of which the model may overfit on that particular data. If you allow certain misclassification, then there is a chance that you may not get 100%, but you may get 80%, 90%, even on the training and the test both. So in that case, that model would be a better model when compared to the previous model. Right. So this particular and the cost function and epsilon, the way they have configured internally, it will allow some misclassification. You need not to worry about that cost function and epsilon to configure. So that the way they have configured internally in the backend, so it will allow some misclassification, either to high cost function or to low cost function. But even if you want to change it, there is a provision you can go and change that in the argument.
And so that sigmoid is the one that where we have that S curve, correct? The kernel
Yes,
sigmoid.
yes.
Okay.
So basically, we use sigmoid, when we want to have some kind of S-shaped uh, boundary or the hyperplane. In that case, you can go with the sigmoid. But see, as I mentioned that, basically we use SVM when we have a larger data set. So you cannot view that data, what kind of decision tree would fit to that particular data. So it's just a hit and trial. Okay. So you try various kernels and see which kernel is giving you the better result and then go with that.
Okay. So you're saying for any kind of, the data set that we get, we should try to apply all the type of kernels
Yeah. Yeah.
as a hit and trial.
Yeah. yeah. So see, again, first try the simpler, go with a linear. Okay. If the linear is serving your purpose, then no need of, going with a complex transformations, right? Complex kernels. Because the complex kernels may again, lead to an overfitting. Okay, so see that which particular kernel is giving you a better results on training and test, consistent result on different new data sets. So
Yeah.
try cross validation. So in the cross validation, if you are getting consistently in every fold, you are getting a better results, then go with that particular kernel. So try with a simpler model, a simpler kernel, and if that satisfies your need, then no need of trying other kernels. But if you're not getting better accuracy with the linear or the sigmoid, then go with polynomial and then finally try the RBF. RBF is the most complicated and the uh, complex transformation. in SVM.
Okay, more complex than sigmoid, you're saying.
Yes, sigmoid is more of a S curve, but this radial basis function is something like, it will find out the sphere or the circular kind of decision boundary.
Okay.
So that's the thing. Got it?
Yeah, I'm fine. Yeah.
Any other questions, guys? Okay. All right. So today we are going to discuss about one new topic known as ensemble learning. Okay. So what is ensemble learning is, see, by now you have seen that each and every algorithm, the way it works, and for every use case, we tried one single algorithm, right, and trained one single model. Um, Now you might be thinking, why can't we apply multiple algorithms on the one single use case uh, and try to use all the algorithms or all the models together? Okay, how can we combine all the models together and get the best of all the models? So ensemble learning will allow you to do that. What it does is, if you have a lot of different heterogeneous algorithms. Heterogeneous algorithms means a different algorithms which works in a different way. For example, you have logistic regression, which works, you know how it works. Then we have KNN, then we have naive Bayes, then we have discussed about decision trees, and yesterday we discussed about SVM. So these are all different models, okay, which you can train separately and then combine together, okay, to have one single meta model, okay. So this particular, so see, think about a scenario where, let's suppose you have to give a test, right? Now, let's suppose every individual is attempting for that test individually, okay? In that case, probably they may not score that high if they don't have a better knowledge on that particular subject, or if they haven't done a strong preparation, if the learning is not that good on that particular subject. But if you allow these people to sit together, okay, and then solve that particular problem, probably, they may score well, right? Because every person, may complement each other, right? Few people may be good in certain areas, other people may be good in some other areas, right? If you allow them to sit together and then apply, when we say, right, we do combined study, we go and uh, if we attempt any kind of test, or we go and build any kind of project together with different skills of people, we generally do better, right? So here also, every algorithm is in itself is unique, okay, which learns in a different way. So here we can combine all those models together, to get a better results. So for example, if I have a binary classification problem, so this linear regression may give me, let's suppose, class 1 as an output for a particular observation. KNN is also giving me 1, okay, but other 3 is giving me the output as 2. So I'll go with a majority vote. Out of these 5 algorithms, if majority of the models are giving me the class 2 as the output, then my meta model will give the classification as 2. So in this way, I can improve my results because I'm taking the what do you say, the best of all the models, right? Um, so certain patterns, probably logistic regression miss out. Certain patterns, probably other algorithms may miss out. But if we combine all the models together, we can get better results. So ensemble learning in short is, if you combine multiple models together and try to predict the observations, in that case, you will get a better results. And each of these models are, in ensemble learning called as weak learners. Weak learners because individually, if these algorithms or these models are not capable of giving you a better accuracy, then we combine all these weak learners together to get a better results. So this is the final trial, okay, what you can do, to improve the accuracy. If none of the models are giving you the better results, so you can stack all those models together and then you can uh, try uh, making the predictions. Okay. So So what is ensemble learning now? Ensemble learning in general is a model that makes prediction based on the number of different models. By combining individual models, the ensemble models tends to be more flexible, less biased, and less data sensitive, which is less variance. So I think I haven't spoken about the bias and variance trade-off, so I will cover now. So that bias and variance problem can be solved through this ensemble learning. So now what is that bias and variance? So this curve looks like this. So bias and variance, the main cause of errors in the model is because of bias or variance. So let us understand, what is bias and variance. So see now in the data, if you have one majority class, right, and for other class we have very few observations, which we call as imbalanced data, your model may tend to get biased towards the majority class. Even if I give you, like, if I ask you to classify between two categories, but I will show you one category more number of times and other category very few times, then the majority category will stay in your mind uh, because I have shown you a lot of times, and the minority category may not be that you cannot memorize that well, and in that way, probably you will able to categorize the majority category better when compared to the minority category. So you will be biased towards the majority category. Same way in the models also, if your data set is imbalanced, your model may get biased. So there are many other ways of getting biased. Other ways are, like, for example, in the numerical prediction, if you have considered a similar patterns more number of times, then again your model will become biased to those patterns only. So, however, you will give the data, whatever way you will give the data, in that way only the model will try to learn. And you know that how these models will learn. Okay, so we have discussed about all these algorithms. So, the model, there is a chance that model will get biased because of the data, because of the variables, because of the observations, or because of the categories. There could be numerous ways through which the model can become biased. And if it is becoming biased, that may lead to an error, right? So similar way, the variance is if your model learn too much. Okay, so every small patterns also, if it learns, it tries to learn, then again, there is a high chance that if there is a small variance in the data, okay, it may lead to an error. Okay, so basically, if we call error here, so this is my bias, and this is my variance, and this is the model complexity. Okay, so what will happen is, if I take a simpler model, okay, which is less complex, there's a high chance that it may have high bias, because of which the error may increase, right? If I take highly complicated model, then it may try to learn every small patterns. We will talk about neural networks in the subsequent classes. So there you will see that it will try to learn all the hidden patterns existing in the data. Okay, so in that way, the variance could be high, because after learning too much, so it will try to predict every minute it will consider every minute changes in the values, when it comes to the input features. So there could be high chance that it may vary too much, okay, with a small change in the value. So because of which the error may increase. So we have to take a trade-off between the bias and the variance, and we have to choose a model somewhere here, where my error is minimum. So it depends on the case to use case to use case. In depending on the data set, you have to choose whether there is an error because of the bias or because of the variance, and you have to choose the model which is somewhere which can reduce the bias as well as the variance, and which will give you the better accuracy. So one such way of reducing the bias and the variance, and which will balance these two components, is your ensemble learning. Because when I'm combining multiple models, one model could be complex, another model could be simpler. So if the simpler model is increasing the bias, if the complex model is increasing the variance, so if I combine all this thing together, somewhere, it will get balanced out. Okay. And as I'm taking the majority vote out of these models, so this bias and variance will kind of get balanced off, and I can get a better results. So by combining individual models, the ensemble models tends to be more flexible, which is less bias, and the less data sensitive, which is less variance. Okay. So there are three types of ensemble learning techniques. One is stacking. The one which I have discussed is known as stacking. So stacking is an ensemble method where the output from the multiple classifier is passed as an input to a meta classifier. So it looks like this. So you have a training data, you created this particular model. Here also you have at the level 0, you train multiple different classifiers or the models, and you take the output of each of those classifiers. Either you can take the majority vote here, or else you can train a altogether a separate model over here, on the output value of each of the classifier. This we call as a meta model. But typically what we do is we just take the output value, and we generally use the stacking for classification problem, and we go with a majority vote. If out of 5 models, the three models are giving me the output as class 2, then I will go with class 2. Okay. So like that, I will make the predictions, and then I will compare with my actual values and see that now whether I'm getting a better accuracy or not. If I'm getting a better accuracy, I'll go with this ensemble models. So I have to deploy all these models in production when I'm going with stacking. So every time the new data will pass through each of these classifier, and I will get the predictions, and then I will combine these predictions, and then I will go with the majority vote. That would be my output value. Or else I can train a separate model altogether on these output. Okay. And based on those output value, I will generate a new predictions. So this is the basically a stacking. This is again in ensemble learning. Again, this is a very last option. So there are other techniques also, which is bagging and boosting. So what is the difference between bagging and boosting? The major difference between the bagging, boosting, and stacking is that in stacking we can go with a heterogeneous models. Heterogeneous models means a different algorithms I can train, and then I can combine all those models, and then I can make the prediction. So that is a stacking. Here in this bagging and boosting, I will go with homogeneous models. Homogeneous models means I'll only go with one single algorithm, but I will train that algorithm multiple times. So I'll build multiple models by using the same algorithm. For bagging and boosting, we generally go with decision tree algorithms. And there is a difference between bagging and boosting. The major difference is that in bagging, these individual models are trained parallelly. So I'll explain you in detail. Uh, while in boosting, these models are trained sequentially. Okay, so now let's understand, how this bagging works. Okay, first. So I have a data set. Okay, I have a data set on which I have to train the model. So what I will do is I'll randomly take multiple samples. So whatever number of models I have to train, that many number of samples uh, I will create, from this particular data set. So let's suppose one subset is is here, okay, on which a particular decision tree is been built, and there would be another sample, another subset on which another decision tree will be built. So like that, there will be multiple trees, okay, parallelly will be built, from this particular random samples coming out from this data set. So this decision tree will fit on this particular random sample. This decision tree will be fit. So here the random sampling is not just the observations, but also the fields. So let's suppose you have 20 columns and you have 100 rows. So here we can decide how many columns should be considered in the sample. So let's suppose I'm going with k equal to 10. Okay, so 10 columns. So randomly 10 columns will be selected in this particular subset. Randomly 10 columns will be selected in this particular subset, and even the observations, right, randomly get selected. So every sample would be unique because it will randomly pick up, certain columns out of the data set and certain observations from the data set. So every sample would be unique, and on every unique sample a decision tree will be built, okay, will be trained. And now again, so now these decision tree will be considered as a separate models. Each of these decision tree may not give you the desired results, but if you combine all these decision trees together, and in the same way how in stacking, we are taking the predictions from every single model and then combining together and to get the final prediction, here also we will do that, the same thing. So in the numerical prediction, what we will do is if we have multiple models, we take the values. For example, this has given me 10, this is 12, this is 14, this is 15. I'll take the mean. So I'll combine the output of all the models, and I'll take the mean. That would be my final prediction. If it is a classification problem, then I'll go with the mode. So mode is nothing but the majority vote, okay, or the category which is having the higher frequency, that is considered as mode. That would be my final output. So here, one decision tree is not dependent on other because all these decision trees are being trained parallelly. So random sample will be generated and then parallelly the decision trees will be built. There wouldn't be any kind of relationship between each of these decision trees. Those are independent models. While boosting, what happens is this one single data set will be passed to one decision tree first. Now this decision tree will be built. Now on this decision tree, the evaluation will be done, and it will see that on which all observations it has done mistakes, okay, where the errors are high, okay, and those wherever in which for whichever observation the errors are high, higher weightage will be given to those observations. Now that particular data set, adjusted data set, here in the beginning, all the observations will be having the same weights. Okay, so this decision tree will give emphasis on all the observations equally. But after it is trained and evaluated, now the observations where this particular decision tree went wrong, or where the misclassification happened, where the errors were high, those observations will get higher weightage. Now that adjusted data set along with the weightage will be passed to the next decision tree. Now, this decision tree will focus on mostly on those observations where this first decision tree went wrong, where the errors were high, and it will learn from the mistakes of the previous decision tree. Now, it will try to improve the predictions of those observations where the first decision tree failed, right? And again, again, it may not able to solve all those errors. So it the second decision tree would also fail somewhere. So now where the second decision tree failed, again the weights will be updated. Okay, then adjusted data set will be passed to the subsequent tree, and like so on. It will keep on adding more decision trees until and unless, it gets a better results. Okay, overall, a better accuracy. So now here it is sequentially. Here the decision trees are dependent on each other. So here the decision trees are getting built, one after the another. So in sequence. So here the second decision tree is dependent on the first decision tree. So where all the first decision tree is making errors, it will pick up those errors and it will try to improve, or it will try to improve the accuracy, overall accuracy of the predictions. Okay, so and then again, the third decision tree will learn from the mistake of the decision tree two, and that's how it will keep on going until and unless it will get the better overall accuracy. So that's the difference between the bagging and boosting. The first difference is that in bagging, the decision trees are built parallelly, and every decision tree is independent to each other. In boosting, the decision trees are trained sequentially, and the decision trees are dependent on each other. Okay. So now these are the techniques. The bagging is a technique and the boosting is a technique. So in this bagging and in this boosting, again, there are multiple algorithms which works on this particular uh, which uses this particular technique. So for the bagging, the most popular one is the random forest. So random forest is the name of the algorithm which uses this bagging technique. So why it has named random forest? So forest, you know about, right? So multiple trees we are training here. That's the reason it is named as forest. And we are taking the random samples, right? We have seen here. So we are taking the random samples, subset 1, subset 2, subset n, right? So that's the reason it is called as random forest. Here randomly the trees will be trained. Okay. You can give number of trees as 10 or 100 or 200, okay, that many number of decision trees will be trained on the random samples coming out from the data set. And here you are generating multiple samples, and based on multiple samples, multiple trees will be trained. Okay, and from each of the tree, the predictions will be made, and then it will go with the majority voting, and then it will be the final predictions will be made out of that. Okay. So here, if you see, we have 9 different models. Out of 9 different models, 6 are predicting ones and 3 are predicting zeros. So final prediction would be 1. Okay, this is a simple concept, right? So all these models individually are called as weak learners. Weak learners, see how you will decide whether you should go with an ensemble learning or not. You will try various algorithms, you will train the model, and you will test the accuracy. And if the accuracy is not good, then only you will go for ensemble learning, right? So basically, when they are not giving a better accuracy, that means these algorithms couldn't able to learn all the patterns properly, right? So these are considered as the weak learners. And when we combining all these weak learners together, so they are becoming strong, right? Overall, they are complementing each other, and the overall um, model together, this random forest is kind of taking the best of all the different models together and giving you the better prediction. So it is the combination of homogeneous weak learner models, okay, which together is giving you the better prediction. So what is the procedure for training this algorithm? You first select how many number of trees you would like to train. So that many number of subsets you have to consider. For example, I'm selecting n equal to 1000, random subset. So now it will train 1000 decision trees on each of these random subset. Okay. So the optimal split of each decision are based on the random subset of the features. So let's suppose 10 features in total. Okay. So if I put as even the number of features I need to mention. So if I mention 5, it randomly select 5 out of 10 features to split. Okay. Now, each individual tree predicts the record candidates in the test set independently. So, as I mentioned in the bagging in the random forest, every tree is independent, which is being trained on a separate sample of data, right? Um, so now these are independent. So each of these individual tree will predict separately, and then we will combine all those predictions together to make the final prediction. For each of the candidate in the test, random forest uses the class with majority. So that we have seen, right? So this is a very simple procedure, okay? Uh, but it would take time because it has to train multiple decision trees. So generally it will take a lot of time. So if you are putting it as 1,000 trees or 100 trees, so just imagine, okay, it has to train 100 different decision tree models separately, okay, one after the another. So that's the reason it will take a lot of time. Okay, so this is again a different representation. So it will take a random subset of features to split the tree. Again, it will take the random subset of features to split the tree. So every decision tree is unique and independent and will be trained parallelly. And then the predictions will be combined together, and based on the major voting, it will do the final prediction. Now comes the boosting part. So why we are saying boosting here is, uh, see, the bagging full form is, if I remember correctly, it is bootstrap aggregation. So basically, the full form is bootstrap aggregation. So BAGG. Okay, so these alphabets they have combined together, and named it as bagging. So bootstrap aggregation is nothing but bootstrap means it will take the random samples from the data and then we are aggregating the output. So that's the reason it is called as bagging. Okay, so why we call as boosting? Because every time a new decision tree is being built, it is boosting the overall accuracy, right? So here, let's suppose if the accuracy is 65%, now after adding this decision tree, it may increase to 70%. Now after adding one more decision tree, it may increase to 72%. So like this, every time a decision tree which is getting added, is trying to improve the overall accuracy. So that's the reason it is called as boosting. So in the boosting, again, there are multiple algorithms. We have AdaBoost. Okay, we have SGBoost. Okay, so there are multiple techniques. So AdaBoost and SGBoost are, and then we have gradient boosting methods, GBM. Okay, and after the GBM, people have came up with another algorithm known as SGBoost. So SGBoost is gradient boosting technique, extreme gradient boosting technique, which uses again the gradient descent. Okay, so I will explain you what it is. So how the second decision tree, how it should take, um, consider the mistake of the previous decision tree. So that approach changes from each of these in each of these algorithms. So that's the reason, it has been um, so these algorithms are kind of considered as a separate algorithms. But overall, what is happening is every tree will try to boost the overall accuracy. But how because as it is a sequential, right? How this particular information of the previous model is passing to the second model, that technique may change, okay, from algorithm to algorithm. That's the only difference. But overall, the boosting will happen. Every time a new tree will get added, it will try to boost the overall accuracy. So now in AdaBoost, how it happens? So the overall data set is passed to this particular decision tree. Now it will calculate the weighted error rate of decision tree 1. Okay. Now after calculating the error rate, now it will calculate the overall tree's weight in this particular ensemble. Okay. So currently it is only one single model. Okay, so it will just calculate the overall tree's weight and then increase that weight for the wrong classified points. So how it will happen, I'll just give you a simple example. Let's suppose I have 10 observations. I have 10 observations. So every observation weight would be 1 by 10. Okay. So now what it will do is it will find out the overall error, okay, of this particular. For example, out of 10, 3 went wrong. So 3 by 10 would be my error rate. Now this error rate, for example, these 3 went wrong. So now in the second phase, the weights of these 3 observations would be higher when compared to these other observations which were correct. And now those after these weights get updated on this particular data set. Now this new data set with the updated weights will pass to this particular decision tree. Now again, this tree will be built. Now this time the tree will emphasis more on those observations which went wrong, in the previous model. Okay, so now it will emphasis more and it will try to improve the accuracy for these particular wrong classified observations. Now again, there could be possible that out of 3, now this second decision tree uh, could able to predict only 1, okay, out of these 3. So now those observations which have been misclassified by even decision tree 2, those will get even higher weightage. Okay, so now it becoming ensemble, right? So ensemble means nothing but the collection of multiple models. So it will give more weightage where the previous trees couldn't able to predict correctly. Okay, now like this, the weights will be passed on, to the subsequent trees, and then overall the accuracy of the model will get boosted up, okay, as it moves forward. So this is basically the step-by-step process of updating the weights. Okay, so for example, if you have 100 data points, so firstly it will initialize the equal weights, which is 1 by 100. So 0.01 would be the weight for every observation. It will train the decision tree. Once the decision tree is trained, then it will calculate the weighted error rate, which is E of this decision tree. Uh, it's just like how many wrong predictions out of the total uh, predictions happened. So that is your weighted error rate. You treat the wrong predictions differently based on the data points weight. Higher the weight, the more the corresponding error will be weighted during the calculation. So now this is the error rate, which is nothing but the wrong predictions divided by the total predictions. Now the weight of the tree is given by this, okay? So learning rate is the fixed constant value into log of 1 minus e. So this mathematics you can ignore, okay? Nobody is going to ask you. So this is your weight of the entire tree. Now what will happen is, yeah, so you have this old weight, which is this 0.01, and this is your weight of the tree, okay? So you use this particular technique. You take the exponential of this weight of the tree, which is coming out by this particular formula, and you multiply with this old weight. And that's how, for the wrong data points, the weights will get updated. And now you pass this particular data with the updated weight to the subsequent decision tree. And now that decision tree will focus more on those observations. And all these things is being configured under this random forest algorithm, which will in the AdaBoost algorithm, which will automatically will emphasis more on the observations where the weights are high. So you need not to worry about that, how this particular decision tree will focus more on those observations. Okay, so it is taken care uh, in the algorithm itself. Okay, so now here the decision tree will get better, every time. Okay, and every decision tree will focus on the complex or the difficult observations where the previous observations are not performing better. And then overall, it will give you the weighted majority. Weighted means overall, this particular, the last decision tree, here, all those weights and everything is been finally calculated. Okay, and whatever the predictions you will get out of this model, will be passed to as a final prediction. So but the input observation will pass through all these models sequentially. So let's suppose now, because see, when you are passing the new data set, it doesn't know whether it is right or wrong, right? What is the actual prediction? Because that is not available, right? So when you are passing the new data set, now this model will give some prediction. Now this model will give some prediction. Now this model will give some prediction. So like this, every model will give some predictions. Now again, it will take the majority vote of all the models, and that would be your final prediction. But while training the way it has trained, so all the mistake what this particular decision tree has done, it has learned. Now then again the subsequent tree has learned. Then like that, the tree started learning all the previous mistake what the earlier decision trees have done. So that learning is a sequential learning. Now this input data will be passed through all these decision trees. It could be a case that this first decision tree may predict that correctly. Okay. So if it has predicted correctly, that means in the training data set also, it might have predicted correctly observations which are having the similar patterns, right? In that way, this particular decision tree would also might have predicted correctly. So overall, whatever decision trees sequentially have been trained, we take the predictions of all those decision trees and then we take the weighted majority vote. Okay, so that's how this ADA boost works. Now, when it comes to gradient boosting, it works on that particular concept known as gradient descent, which we have discussed, right? Overall, what it will do is it will try to reduce the cost function. So rather than updating the weights, okay, what it will do is the gradient boosting. So gradient boosting, right? This is a convex function. Okay, it will start, for example, this is one decision tree which has been trained. Oh, sorry. Decision tree has been trained. Now, what it will do is the gradient boosting, it will try to, it will, again, there would be some mistakes because of which the errors are high. Now, this gradient boosting will help this decision tree to learn in such a way that this overall cost function will get reduced. So like that, multiple decision tree will be trained eventually to make sure that the errors are coming down. And that's how, here it will work. So the first decision tree will be trained, predictions will be made, the residual errors will be calculated based on the difference between the actual and the prediction. That would be your residual error. So now that residual error by decision tree will be passed to the second decision tree. Now here the gradient descent will try to improve the cost function, which is this residual error. Okay, so that this decision tree is better than my previous decision tree. And again, it will be checked. Again, the residuals will be calculated. Again, that will be passed to the subsequent tree. So here again, the boosting is happening. Step by step, the overall accuracy of the model is getting improved. So the accuracy is getting boosted. But here the technique is different. There, the more emphasis was in ADA boost was on the data set, right? In the data set, the weights are getting updated and that is getting passed to the model. Here, the errors are getting passed to the next tree or the next model to improve the overall accuracy. The only the techniques are getting is different, but the whole concept is still the same. Okay. Now, this is known as gradient boosting technique, and on this there are multiple algorithms. One is like GBM, we call as gradient boosting models. Second is SGBoost. SGBoost, computationally, they have come up with this particular algorithms which can work on a larger data set. Okay, so the way this program runs is so there is the way the data is getting stored and the gradients are getting calculated. So they have used some faster computation uh, in the program, which can do all this gradient calculations and all those things much more faster than the GBM in the GBM algorithms. So GBM algorithms are a little slower when compared to XGBoost. Now, if you might have seen, gone through this Kaggle, you will see that in Kaggle, in most of the competition, people use XGBoost. Now, it is also called as a favorite model of a data scientist. Okay, because this XGBoost give a very high accuracy. Okay, because see, every time the decision tree is picking up the errors from the previous model, and it is trying to improve those errors, okay, or to reduce those errors. So as a concept, this is a very powerful concept, right? It is trying to reduce the errors step by step, and overall, it will try to improve the accuracy. But again, you have to be cautious because it may lead to overfitting, right? So you have to make sure that how many trees you want to build. If you just allow this tree to the number of trees to be get selected automatically, then it may give you 100% accuracy. If it is 100% accuracy, there is a high chance that it may lead to an overfitting problem. Okay, so yeah, so XGBoost is considered as the most favorite model of the data scientist because it will give you a very high accuracy, even better than SVM. Okay, so the step again, we have just limited steps here also. We have to train the decision tree, apply that decision tree, get the predictions, calculate the residuals, errors, and then those residuals errors, we pass it to the second decision tree, and again, the decision tree will be trained. So like that, it will repeat. And then based on that, we will make the final predictions. Okay, so that's about ensemble learning. So I'm sharing you all the concepts. Okay. So just remember these concepts, and now the biggest confusion would be when you are working on the real world use cases. Now there are too many techniques or too many algorithms. So you have multiple choices. So picking up the right selection of the right model is going to be a challenge, right? Again, in the boosting and in the bagging, again to choose. Bagging is a technique which will also provide you the feature importance. You might have seen that in decision tree, we can able to rank the attributes. Okay, the attributes which are selected first are considered as the most significant attributes, right? So you know, right, how the attributes are selected in decision trees, right? Based on the Gini score, based on the entropy, we can select the attributes. So the attributes which have been selected in the beginning, those are considered as the important features, right? So in the bagging, as it is a separate independent decision trees, so what it does is it collects the important features from all those decision trees. And then it will see that in most of the decision trees, which of the features are common, right? Which have been selected as an important feature. And based on that, it will give you the feature importance. We'll see in the code. So one ask from the business or from the stakeholder could be like, okay, when you have trained the model, which of the features have been considered as highly significant or which of the features have been considered as important? Then you can give that feature importance through this bagging or through this random forest, which will again give you a additional insight about the data, right? To predict, for example, customer churn, which of the features are considered as most important. And now the business can focus on those, and they can they can reduce the churn by focusing more on those particular variables which are impacting the churn, right? Similarly, in the life sciences, for example, if you're predicting the heart disease, so for predicting the heart disease, the model has given high significance to what all variables. If you're able to understand, then you can get the insight that these are the features are impacting the uh, patient's health, and because of which they are prone to heart disease. And now, if you provide this insight to medical practitioners, they can focus more on that particular patient by knowing that, okay, these are the features could be the probable cause of this heart disease. So one way is like prediction. The second important thing is like explainability or interpretability of that particular models. So if the model is getting trained and giving the predictions, on what basis it is giving the predictions, on what features it is giving more emphasis. Okay, if you are able to understand that, it will give you the additional insights. And even just not the predictions, but also the root cause analysis, we call it as RCA, or even to do some kind of um, uh, preventive measures if you have to take. So these kind of insights would definitely help the business to make better decisions. While in boosting, we cannot do that. Boosting will give you the higher accuracy, but it will not give you the feature importance. So that's where you have to choose in what kind of use cases, what kind of techniques to be chosen. If the purpose is to get a higher accuracy, so basically in this Kaggle competition, the main objective is to get the a higher accuracy, and then only the people will get ranked high on that leaderboard. So people generally go with SGBoost. In most of the competitions, the people who have won that competition, they have used SGBoost. So if the accuracy is the only objective, then you go with SGBoost in the boosting technique. Okay, that will give you the higher accuracy. If you're going with an individual algorithm, then go with SVM or go with the neural networks. That will give you a higher accuracy. But again, as I mentioned, this bias versus variance trade-off. As you're going with a more complicated model, though it will give you the higher accuracy, but there could be a chance that it may be more, um, it will get affected by the variance in the data. Okay, if there is any little change in the data value, okay, it will give you completely different predictions. Okay, so that kind of a trade-off needs to be taken care, and that is the job of data scientists, guys. Otherwise, everything, all these things can be automated, right? We can have one single tool where the data can be passed in. Okay, all these algorithms can trained automatically, and it can give the predictions. So even there are like certain platforms which we call as auto ML platforms. So auto ML platform is here. Even the business users who have limited knowledge about data science, or even the people who have no idea about programming, they can train the models. So we have platforms like Data Robot. Okay, you can look into this. Data Robot, Data IQ. Okay, on Azure we have Azure ML. On AWS we have SageMaker Auto ML techniques. So here you just pass the data, okay, and this platforms will train all the algorithms, and it will give you the entire report of all those algorithms. Like logistic regression is giving you this much accuracy. You can even select the algorithms. You can select logistic regression. You can select naive Bayes, whatever. Let's suppose SVM, and then you can select random forest, SGBoost. You can train all the models through UI, okay, just by passing the data, and it will train the model, and it will give you the comparison of all those models. And now you can select which model is giving you the best results. So here the real knowledge on the algorithms and even the programming skills are not required. It's completely low code and no code platforms. But where the data scientists come into picture is, and again, these are expensive platforms, right? So no customization can be done on this, okay? But here your intelligence come into picture, right? If you have a data set, what features to select, what transformations needs to be done, how to improve the quality of the data, how the data curation has to be done. All that thing is like manually people need to think about, right? That's where the data scientist come into picture, and that's the value of data scientist, which he will bring onto the table, right? So first is on the data part. Now comes the algorithm. Okay. Now, depending on the case, depending on the ask of the business, now you have to decide which algorithm to use. Now, again, in the algorithm, there are fine-tuning techniques, right? So again, how to fine tune, how to use the right hyperparameters, values, so that you will get the optimal result. That also something manually people can think, okay, that cannot be automated, right? So there are certain areas where the automation is not possible, where the human judgment and human thinking and human intelligence is required. So you have to gain the skills more on those aspects. Okay, and that's where, otherwise model training is can be automated, but the other things around it, where where the skill of data science come into play, like choosing the right algorithm, reducing the bias, reducing the variance, okay, and improving the quality of the model output. So that's something you have to do on your own. Okay, and that's the value you have to bring it, okay, onto the table when you're working on any project. All right. So, any questions?
Would you be running a use case for this on Python?
Yes, yes. So, what I'll do is I'll run it tomorrow. Okay. So first, you guys digest this particular thing. Okay. Go through this concept, and tomorrow we will take the use case. Okay. Is that fine?
Yeah.
Any questions? Any concerns? Anything would you would like to discuss, guys? And see, after once I complete the supervised learning, I'm going to ask you a few questions, guys, and I would like you guys, to answer whatever questions I will ask. At least attempt answering those questions. So with that, I can able to understand, I can gauge right how much you are getting it. It's okay if you are wrong, it's fine. Okay, so don't worry about it, but try. You could be correct also. Okay, so people hesitate in answering just with the fear that they may go wrong. But there is other side also. Okay, what if you are right? Right. So think about, always be positive. Okay, always be optimistic. Think and have confidence on you. Whatever answer you have, think that okay, that could be correct. And don't stop yourself just by having a fear that I may go wrong. Right. It's okay if you go wrong. If you go wrong, then you will be corrected. If you keep that inside, how would you correct yourself? So I'm saying this is a platform, guys. Whatever coming into your mind, whatever your thoughts are, please share it. So here you are not getting penalized, right? If you do the same mistake in the interview, then you have to pay the higher cost, right? So I'm saying better you participate here. Okay, I'm going relatively slow now. Okay, I could have completed the use case also in this class, but I don't want to do it because I want you guys, to first again go through this recording, understand this concept, then you can relate whatever things have been done in that particular code, right? So, but take this time, if you have any, I don't know why you guys are not asking any questions, because in other batches, people like, have so many questions like how to study, how to improve, how to prepare for the interview, how to practice. But you guys are kind of, very silent batch. Okay. You are not asking any questions. So I'm unable to understand whether you are getting everything or you're not getting anything. I'm seeing only very few people, they are just responding while others are just silent. So that's not going to help you guys, to be frank. Okay. So take, as you have invested, you are investing time and money. So take best use of it, right? I don't mind answering the same question multiple times. It's okay. I'm used to it. And as I mentioned, have proper schedule. Daily, please revise the concepts. Okay. Uh, have it in your schedule. Okay. So don't give a break to this. If you consistently revise, consistently study and practice this subject, okay, it's not a rocket science. It's just like, very smartly, you have to understand this concept. You have to relate it to your real life. If you relate it to your real life, it's very easy to understand how it works, right? So what is this ensemble learning? And we do it most of the times, right? We say that, okay, in the exam, probably if the internal test you say, right, okay, you sit with an intelligent person, right, or you create a group and then you attempt the exam, right? The same way here, ensemble learning. All the weak learners are sitting together, all the weak learner models we are stacking together, and we are improving the overall accuracy. So that's how you have to understand. Okay, if you understand the technique of these algorithms, it's easy. But if you go and if you get a fear like, oh my God, so much mathematics, so much complicated. Okay, how I will learn it? So that would not help. And as I said, mathematics is okay. It's in your. I will share enough material if you want to learn mathematics, you learn it. But that is not something, okay, interviewer would look out for. As I said, more emphasis you put it on the application side. You go in Kaggle, look at the different use cases, how people are solving those particular problems, how they are pre-processing the data set, how they are training the model, how they are doing the fine tuning. All that thing, you have to practice. If you go and see 5 or 6 use cases on Kaggle, you will get an idea. Okay, there you can search by algorithm, there you can search by domain. There's a lot of solved use cases, you will get it there. Okay, so my advice is do that. It's just a matter of 1 or 2 months, right? So please put your efforts, do some hard work, and definitely it will, you will get returns, good returns from that. Okay. All right, guys. If no other questions, then I'll wrap up. Okay, so let's connect tomorrow. Thank you, guys. Have a nice day. Take care.